Hello everyone, welcome back to the lecture series on foundations of deep learning, concepts and applications. In my previous lecture, we were discussing about the distributed text representations, then we have seen word to vec model with the continuous bag of words and the skip-gram model. In today's session, we will continue with the word embeddings in NLP, and the contents for today's session are glove embedding and FastText embedding. So, we will see what are these embeddings and how they are different from the word to vec embedding. Now, what is this glove embedding and what is the significance of this one? So, the key idea is learns the word vectors from a global word co-occurrence count. So, the ratio of the co-occurrence probabilities encode the semantic relationship. So, what do I mean by that? Any word or a pair of words or a 2-3 words together, it the number of times these words are occurring together, that gives me a very important information about the semantic relationship between them. Okay. So, we will see step by step when we go ahead, we will see how this semantic relationship is being captured. So, it is basically an unsupervised algorithm that learns unsupervised algorithm for learning dense word embeddings, and it uses a global co-occurrence pattern from a large text corpus and captures the semantic meaning and relationship between words. Now, we will see how this glove works. Suppose I have a text corpus where I have sentences like I like ice cream, I like chocolate ice cream. Okay. So, this is the complete text from which word relationships will be learnt. Okay. So, I do not have anything else, I have two sentences, I like ice cream and I like chocolate ice cream. Okay. So, these are the two sentences that I am having. Now, what is the vocabulary? What do I mean by vocabulary? It is the unique words that are present in these two sentences. So, there I get I like ice cream chocolate. Okay. So, this is my vocabulary. Then I am taking a context window of 1, that means I will see even when I take any word like ice cream, in the first sentence suppose I am taking the word ice, then I will look 1 on the left, 1 on the right, that means 1 word on the left, 1 word on the right. So, that is my context window of 1 size. Now, we will calculate the co-occurrence matrix Sx. So, as I was telling that the semantic or the meaning relationship is captured based on the co-occurrence of the words. So, for that one we calculate something called as the co-occurrence matrix in gloves. Okay. So, what are these? So, I have given a table here, we will understand what exactly all these things are here. So, basically the words that are there in the row, these are my target words, and the words that are there here in the column top, they are my context words. Okay. So, we will see how exactly I am getting these values. So, target word means I will take that word and then I will see on the left side and right side how many times I am getting this context word. So, we will first start with the word I. Now, this I, if you take in both the sentences I and then see left side and right side, how many times we are getting another I on the left side? We are not getting any time. So, I to I is equal to 0. Then I like, how many times I am taking here, then like here. Okay. So, how many times this value will give how many times I and like are coming together. So, I like is coming once in this sentence, I like is coming once in this sentence. So, the number is 2 here. Then I and cream. Okay. So, I and ice. So, I and ice, if I take I, see both left and right side, right side it is like and left side there is nothing. Here also right side the word is like is there, left side there is nothing. That means like I and ice, it is 0. Similarly, I and cream, I and chocolate, both are 0. Okay. Then we will take like and I. That means right now I will take like as the target word, and I will see on both sides of like with how many times I am getting I as the word. So, if I take the first sentence, like, in the left hand side I get I once, in the second sentence also in the left hand side I get I once. So, it is 2. Then like is 0, like ice. So, again like term I take, and in the right hand side I get ice once. In the second sentence, do I get it? No, I do not. So, in that case it is on ice is like ice is only coming once. And similarly, like cream is 0, like chocolate is 1 because I like chocolate, here it is there. Similarly, for ice we have calculated what is the number of times I am seeing the context words. So, for ice is the target word, I have checked for I, like, ice, cream, chocolate, and I have seen ice and I, there is no co-occurrence. Ice and like, there is one co-occurrence. You can check it here in the sentences. Ice and ice, co-occurrence is 0. Ice and cream, co-occurrence is 2. How it is? So, here it is ice cream in the first sentence. In the second sentence also chocolate ice cream. So, here once again ice and cream are coming side by side. So, it is 2, and ice chocolate came here once because ice and chocolate, they are here. Similarly, for the words cream and chocolate, I have calculated the co-occurrence of the nearby words or the context words. Okay. So, you can check the values once again with the sentence. Okay. Then once we have this co-occurrence matrix, we have to compute the co-occurrence probabilities. So, how do we do that one? The first thing I have kept here in this slide of mine, once again the co-occurrence matrix. Okay. And then we will see how to calculate the co-occurrence probability. Now, for that one, what we have done here is we have taken the row sum. Row sum means what? Whatever numbers are coming here, in the first row it is 2. There are no other places where there is any other number other than 0. So, the row sum is 2. Then for the second one, like, the row sum is 2 plus 1 plus 1. Sorry, 2 plus 1 plus 1. So, this is 4. For the third row, it is 2, 1. So, plus 1. So, it is again 4. Okay. So, what we are trying to see is what is the row sum for each of these words. For cream, it is 2, and for chocolate, it is 1 plus 1, which is once again 2. Okay. Now, we have the co-occurrence matrix and we have the row sum. From here we have to find out the co-occurrence probabilities. Why do we want to have the co-occurrence probabilities? Very simple. If the co-occurrence probability is high, that means there is a semantic relationship which is present between those two words. Okay. So, how do we compute the co-occurrence probability? For a target word I, the probability of seeing the context word J can be given as probability of J given I is equal to Xij given divided by summation over k Xik. That means, I am taking the conditional probability of J given I. What is I? I is my target word. So, where are my target words? Target words are these words. Okay. These are my target words which are highlighted in red. Okay. So, for a target word I, the probability of seeing the context word J. So, what is the probability of seeing a context word J is equal to Xij. That means, the number of times I and J, they are coming together, so divided by summation of Xik with all the other words, what is the co-occurrence, and then sum of that one. Okay. So, we will see what exactly is probability of like given I. That means what is the target word here? Target word is I. That means target word is I, and what is the context word? That is like. So, the probability of like being the context word given I as the target word is equal to 2 by 2. How it is 2 by 2? We have seen here I and like, okay, it was 2 divided by the row sum is 2. Okay. So, that is 2 by 2, which is equal to 1. Okay. Then probability of i's given the target word is like. So, probability of i's. So, i's is what? I's is the context word. What is like? Like is the target word. Okay. So, like being the target word, how many times the i's context word have come? So, like is the target word here, and i's has come 1, and how many, what is the row sum? That is 4 divided by 4, which is 0.25. Okay. Similarly, the probability of cream coming as the context word given I as the target word. So, sorry, i's as the target word. So, where is my i's here? I's target word is here, and I will see for the context word cream. So, here is my cream. So, i's and cream, it is 2, and what is the row sum? It is 4. So, 2 by 4, which is half, which is 0.5. Then probability of i's given cream, that means the probability of i's being the context word given cream as the target word. So, cream is my target word. I want, what is the probability of getting i's? So, i's is here is 2, correct. So, 2, and what is the row sum? That is also 2. So, 2 by 2, that is 1. So, like this we can compute the co-occurrence probabilities. Okay. So, what we have done till now? We have made a co-occurrence matrix from the vocabulary, from the sentences we have created a vocabulary. Then we have taken a window size of 1 here, and then we have computed the co-occurrence matrix with the target words in the rows and with the target words in the rows and the context words in the column. And once that co-occurrence matrix have been formed, then we have used that one for computing the co-occurrence probabilities by taking the row sum. Across each row we have taken the sum, and using this equation, the conditional probability equation, we have found out the probability of getting some context word given a target word. Okay. So, these numbers show how strongly one word is associated with another word. So, if the probability is high, that means those are very similar context words, they always come together. Ice cream, okay. Cream chocolate is lesser probable than ice cream. Okay. So, that is the way of computation of co-occurrence probability. Now, we will look into the glove algorithm. What is that glove algorithm? So, if we see to the glove equation, glove tries to find the vectors wi and wj such that the dot product wi transpose wj plus bi plus bj is approximated equal to log of xij. Now, what exactly do I mean by this one? wi is the vector for the target word I, wj is the vector for the context word j, bi and bj are the bias terms, xij is the co-occurrence count. Okay. Xij gives the co-occurrence of I and j together. Now, what exactly we are capturing by this equation is this equation gives when two pair or a pair of words are frequently used together, the dot product is large, whereas rarely used two words together, the dot product is small. Okay. So, and how it is getting captured, we will see it here once again. For that one I have kept the matrix, co-occurrence matrix here with all the red colored words, these are the target words, and the white colored words I like ice cream, which are there at the top of the columns, they are the context words. Okay. Now, we will see how it is coming. So, for the target word ice, where is my ice target word? Here. The context word cream. So, this is my cream. Okay. So, target word ice, context word cream, co-occurrence probabilities, co-occurrence value Xij is equal to 2. So, W ice transpose W cream plus B ice plus B cream is approximately equal to log 2. Okay. That is log of Xij. Okay. That is log 2. Whereas, if you take the other one for the target word ice and the word, context word chocolate, once again target word is ice, same one, context word is chocolate. So, here in this case what is Xij value? It is 1. So, W ice transpose W chocolate plus B ice plus B chocolate is approximately equal to log 1. That means log, of course, log 2 value is more than log 1. So, more the co-occurrence value is, higher is this dot product value. Okay. So, this is the gist of the mathematical implication of glove algorithm. Okay. Now, we will see visualization of glove embedding vectors. So, how do they look in the vector space? So, here if you see, this is a picture where the visualization of the glove embedding vectors are kept, and if you see, there is a pattern. So, if you see the bottom word, each and every vector, there is a bottom word, there is a top word. All the bottom words basically man, sir, king, brother, uncle, okay, heir, okay, emperor, all these basically these are the male version. Okay. Whereas, the top ones are woman, and then sir, madam, then brother, sister, okay. So, uncle, aunt. So, all these are the top words are the female versions. Okay. That means that relationship has been captured in the visualization glove embedding vectors. That means the male figures are coming at the bottom, female figures are coming at the upper portion of the graph. So, this is man woman. Okay. Similarly, I have another graph or the placement of the word embeddings in the vector space, and we see this is the comparative and superlative things. So, if you see dark, darker, darkest, similarly soft, softer, softest, then we have this loud, louder, loudest. Okay. So, clear, clearer, clearest, strong, stronger, strongest, short, shorter, shortest, slow, slower, slowest. Okay. That means there is a pattern. If you see all the placements, there is a pattern in which the comparative superlative terms are placed. So, these visualizations are taken from this source, you can have a look there. So, the main idea here is glove embedding with the help of the co-occurrence matrix and co-occurrence probabilities, it is capturing the semantic relationship. So, any words that are coming together, it is giving more higher probability of occurrence, and these graphs show that it beautifully captures the semantic and the syntactic relationship. After glove, we come for FastText embedding. What is this FastText embedding? It is developed by Facebook's AI research lab, which is called as FAIR. And what is the key idea here? Instead of assigning one vector per word, FastText represent a word as the sum of vectors of its character n-grams. That means, till now each and every word that we were discussing about, each and every word of them, each and every word it was getting one vector. Now, in this case FastText embedding, how it is different from the other text embeddings that we have seen so far, here it does not give only one word. word vector. Okay, it gives multiple vectors of character n-grams. What do I mean by character n-grams? We will see that one. For example, for the word playing with 3 grams n equal to 3, the decomposition becomes the first start token, then PL or PLA. So, each and every time what we are doing is we are taking 3 characters at a time. Okay. So, this is the starting token and then PL. So, together it is 3 characters, then PLA, LAY, AYI, YIN, ING, NG and the N token. Okay. So, we are breaking it into small chunks which are made up of few characters. Okay. The word's embedding is then the sum or average of its n-gram embedding plus word embedding itself. So, it takes all this into consideration and then it gives the word embedding. So, word embedding does not, there is not only one word embedding that is coming from one particular word, it is multiple embeddings are coming from the character n-grams, and together with that one it is taking the word embedding itself, the total words embedding itself, and then it is summing and taking the average, and then it is going further, it is giving us the embedding for that particular word playing. Okay. So, playing, for playing, all these small chunks PLA, LAY, AYI, YIN, ING, NG, last token, all of them will get some embedding. Okay. And those also will be considered for forming the final word embedding. Okay. Now, what is the advantage of this one? Why are we doing this? This makes it better at handling rare words or out of vocabulary words. So, OOV is a very important term in NLP, which is out of vocabulary. That means what is not there in the vocabulary, if those type of words come into picture during the processing time, how your model is going to handle that out of vocabulary or OOV words. Okay. So, we will see what is the advantage of FastText embedding. Suppose during training the model saw happy, unhappy and playing. So, these are the words that the model saw. Okay. Now, it never saw the word unhappiness. So, according to the model's training, the vocabulary for the model is happy, unhappy, playing. There is this unhappiness word is a out of vocabulary term for the model. So, if we take word to vec, for this out of vocabulary words there are no vectors. But in FastText embedding, what is done is, it as it splits into n-grams like with the starting token and UN, then UNH, HAP, APP, PPI, PIN, INE, NES, ESS, SS and then the N token. So, as we are splitting the text, splitting the word into these small n-grams, what we are getting is all these n-grams are having embeddings, and then we sum them to get the approximate but a usable vector for unhappiness, because unhappiness is somewhere coming here. See, from here un is coming, then happiness is coming from all these small chunks of the n-gram embeddings that are coming. So, even though it may not be very accurate, but we have a usable vector for unhappiness, which is unlike in word to vec model, where for any out of vocabulary word there was no vectors. Okay. So, all words which are not there in the vocabulary, there will be no vectors. So, that is compared to that one, this is having a better approach, because at least some usable meaning we are getting for the word which the model have not seen during the training process. Okay. Also, it handles typos like playing instead of PLAYING, if there is a typo like PLAING. So, because it has divided the word into n-gram embeddings, it is able to handle the typos like this. Okay. So, with this one I come to the end of this session, and before I conclude I will do a small recap of what we have learnt in today's session. So, we have started with glove embedding, and we have seen how the glove embedding vectors are formed using the co-occurrence matrix. The co-occurrence matrix is the very important part of glove embedding formation, and how these co-occurrence matrix calculations are happening, and from the co-occurrence matrix how do we find out the co-occurrence probabilities, and what exactly we are trying to get from the co-occurrence probability. It is the probability of a context word given a target word. Okay. So, it is giving the probability of what a context word will come given a target word is given to you. Okay. So, that is about the calculations that we do in glove embedding, and then we have seen the visualization of how the glove embeddings look in the vector space, and we have seen how beautifully the semantic and the syntactic relationships have been captured when we get the word embeddings using glove. And then we have seen what is the mathematical algorithm behind that one, what is the dot product between the words, and how the co-occurrence of two words is helping to get the probability scores. So, that we have seen the mathematical formulation of glove embedding, and then after that we have come to FastText, where we have seen how a word, instead of one single vector coming for one word, how a word is divided into small chunks. One single word is divided into small chunks called as the based on the n grams that are present there. N can be 2 or 3, and those small chunks are coming out of the one word, and we are getting the word embedding for all these chunks, small chunks. And what is the advantage of this one? The advantage of this one is when we are using all these small chunk word embeddings for the final word vector formation for that particular word, what is happening is it is able to handle lot of out of vocabulary words, which we have seen, like unhappiness was not given to the to a model where happiness is given, some other term is given, but unhappiness was not there. Happy was there, happiness was there, but unhappiness the model did not see. But because we have divided the words into chunks, and we have made embeddings and use those embeddings together with the total embedding of the word itself to get the final word embedding for any particular word, it is able to handle those kind of out of vocabulary words. And also it helps in handling the typos that come in real world situations. Okay. So, with this one I come to the conclusion of today's session. In the next session you will have a hands-on session in which you will be going through, or you will be executing some codes for NLP tasks and using these kind of models, and this is my last lecture in the lecture series. Please keep learning, enjoy the course, happy learning, and thank you all.